we will look at the theorem that shows the least squares solution and see how it applies to this. So here's our application, least squares line. If you have a two-dimensional data set, common problem in statistics is the model the line that best fits the data. Finding the line of best fit is equivalent to the least squares problem solution, or least squares problem. Just for the sake of trying to copy the notation they have for statistics, they use the variable beta as a vector, and instead of using A for your matrix, they use capital X. And so I hope that's not too confusing. The Y data is just the output. So you basically have a list of X and Y values, and then you're going to try to make a line out of it. So the notation they have for the matrix X, now X is the matrix, is that X is sometimes called the design matrix. So it turns out that you can apply this not just for linear models, but you can apply it for quadratic models, exponential models, and all kinds of other different types of models. B, or beta, is your parameter vector, and this is what you have to solve for. So depending on what type of regression you're looking for, if you're looking for a line, then line mx equals or y equals mx plus b business. So you need a slope and a y-intercept. If you're looking at a quadratic function, then there's more parameters involved. So your parameter vector will grow depending on what type of model you're trying to use. Y is the observation vector. It tells you your output values. And so in our case, between the points x and y, it's all the y values that come out. So it turns out that the x values of your points will somehow make itself into the design matrix. That's why the matrix is called capital X, is because it's going to hold your x values. The line of best fit that we're going to look at is going to be B naught plus B1, or beta naught plus beta 1 times x. So that's the equation of the line we're going to be looking for. I know we're used to saying y equals mx plus b, but it's the same idea, right? You can figure out that the slope is b1 or beta 1, and your y-intercept is beta sub 0. So this is the best model of points in the sense that this is going to be the shortest distance between the two vectors that we're looking for. The y vector and whatever vector it is that's involved. This line is called the least squares line, the line of best fit, or the regression line. And it's interchangeable, and we say that in statistics as well. So depending on how you hear it, it's the same thing. So the coefficients beta naught and beta 1 are called regression coefficients and can be solved using the least squares methods. So this is like your x1, x2, or your c1, c2, or however you want to consider it. So the method is to match up the predicted y values with the observed values. So the predicted y values would be putting the x value into your model regression line. And then your actual observed values are your y values. Yeah. This is the foundation for how computers learn. And so if you're looking for, I know this class is super theoretical, but if you're looking for application, real cool application of linear algebra, this is the beginnings of it. It gets pretty complicated pretty fast, but it's this super cool in learning how machines are able to kind of take all these different variables and then create a function that measures that cost and then being able to minimize that. It's super cool. So if you're going to go into some sort of computer science type thing, I think machine learning, data science, it's a big field now. You should take this seriously. Yeah. So, and you would imagine that the data that they collect are like thousands of data points. So in our class, I'm not going to collect any more, but in our class, a handful of you gave me your foot size and your heights, and so we're going to use that as an example for this. Well, we'll do one simple example first, but then we'll use the actual data that we collected from us and see how it really applies. And again, this is just a two-dimensional XY set of data, but you can imagine when you collect more data that it would just be more than just two variables. And so there you have it. All right, so the idea is that if you have the points x1, y1, x2, y2, etc., you can find the predicted value, and we still don't know that the parameters b0 and b1 are, the beta 0 and beta 1. We still don't know what they are, but we're going to put it in this model saying that we want our predicted value to be based on these unknown parameters that we're going to try to solve for. And then what we want to do is we want to set that equal to y1. And so this is your system. We have ourselves a system of linear equations. And it looks like we're going to have b0 and b1 as our unknowns. We're assuming that we know x1 and y1, x2, y2, etc., all those pairs. And it looks like there's no coefficient. There's a coefficient of b0 as 1. And so we have a system of linear equations. If we have a system of linear equations, we can always come out with a matrix where, again, the coefficients of b sub 0 is 1, and then the coefficients of b1 are like those x values that we have. And then we have a y values, the observed values on the other side of the equal sign. We can take a look at this as some augmented matrix, a n rows and 3 columns, n by 3 matrix. And you could do the row reducing there, but we know that this is probably and most likely and almost all the time not going to have a solution, right? If we just do the regular matrix. And so if you have an inconsistent system, the best you could do is an approximation. And so you get the approximation. And we're going to get the approximation from our least squares approximation theorem. And I think this is theorem 13, not 14. But I don't know. I think it's 13. Anyways, you have AT times A on one side multiplied with X hat is equal to A transpose times your B vector. At least that's how it was written in the theorem, also in your quiz. But we're going to use X's and betas and Y's this time. Okay. So we'll start off with a simple problem that we can actually write out by hand, and then we'll dive into our foot size and height correlation to see if there is correlation, and see if we can do that using MATLAB. Since I teach statistics and I use Excel quite a bit, I could do it in Excel really super quick, but we'll transfer it to MATLAB so that you can see it how it could be used. All right, well, let's do this example. We have to identify our x values and our y values, and it should be clear from your set of points, right? That's pretty straightforward. Now our design matrix X is going to be, no, there's no arrow there, it's just capital X. Now I have 4 points. Remember that the first column for the linear value of things, our first column is just going to be 1s. And I have 4 points to deal with, so I'll say that I have 4 values or 4 rows for each of these equations. And then I'm going to list down my x values. That's 1, 2, 4, 5. So that's my design matrix. My beta is unknown. So this is a vector beta. It's going to have beta sub 0 and beta sub 1. And again, those are the things that we're going to solve for. And beta itself, if we solve for this, where y, the y vector, is equal to the y values, that's 0, 1, 2, 3. If I set this equation up, a times beta is equal to y, I'm not going to have a solution because this is going to be inconsistent. So what we're going to do is we're going to use the theorem to approximate our solution. Okay? Any questions so far? All right, so I think this is something that we can actually do by hand because it's simple enough and it's not that many variables. So let's actually do it by hand. It looks like we're going to need x transpose times x. So x transpose times x is equal to the transpose of this is going to be 1, 1, 1, 1, 1, 2, 4, 5. We're going to multiply this by 1, 1, 1, 1, 1, 2, 4, 5. And then it's a 2 by 4 times a 4 by 2. It's going to give us a 2 by 2 matrix. With the ones, I think that's going to be 4. 1 plus 2 plus 4 plus 5, 12. 12 again. And then 1 plus 4, 5 plus 16, 21 plus 25. What? I lost 30? 46. Interesting. What can you say about this matrix that we just got? What? Symmetric. This is a symmetric matrix. If you fold the matrix along the diagonal, pretending it's a piece of paper, then it matches. So it doesn't matter what the diagonals are. It just, in this case, the wings are. This is a symmetric matrix. We'll dive into a lot of that stuff in chapter 7. Whew. It's gonna be rough. I mean, fun. It's gonna be fun. So this is a 2 by 2 matrix, which means we should be able to find the inverse pretty easily, right? So x transpose x inverse is 1 divided by the something, and then what do? Switch the diagonals, 6 and 4, negative the wings. All right, what's the determinant? 14? 40, 40? Is there a negative? Oh. Anything else missing? All right, cool. I think we can cancel a 4, or factor out a 4, right? Is this, wait, 46 divisible by 4? No. Dang, too bad. By 2? 1 over 20, 23, negative 6, negative 6, 2. Or whatever it's worth. Maybe you might make our computations a little bit easier. All right, so we got the inverse of that. Let's find out, well, x of t, or x transpose, we already know that. Let's apply x transpose to the y matrix, or to the y vector. So that's 1, 1, 1, 1, 1, 2, 4, 5. And the matrix is 0, 1, 2, 3. This is a 2 by 4 times a 4 by 1. So a result is going to be a 2 by 1. We have 1 plus 2 plus 6. And 2, 8, 10, 25. Okay. So then our beta hat vector, there's too many symbols. is going to be, according to this, the x transpose x inverse times the x transpose times y. And we have 1 over 20, 23 minus 6 minus 6, 2. Apply that to 6 and 25. So I think we can just keep the 1 over 20 out and then do this application. Now what? It's a negative. What? Yeah. I got stuck. Negative 12. I'll buy that. And this is 36 minus 50, positive 14. So as we can take out another 2 here. All right, cool. What? It's what? Oh, it is? Oh, wow. Now you know the answer. Wow, is that a fair quiz? Of course it was. Just different letters here, right? I'm trying to show you it's the same thing. Okay, so what does this mean? I mean, we're looking for, what are we looking for? A closest approximation to the line. What line? What are we, what's the, what? No, not the tangent line. The data set that we have, right? Imagine the data set is a bunch of points, and then this line is, well, a line. So so it looks like I have some points. What are my points, by the way? 1, 1, 0. I don't know if this is going to be any good because I'm not going to draw it to scale properly, of course, because I'm trying to do this by hand. But I have 1, 0. What was it again? 2, 1. 1, 2, 3, 4, 2. 1, 2, 2, 3, 4, 4, 2, and 5, 3. So that's my data. What's my line? I mean, the line of best fit to me, if I eyeball it, being somebody who teaches statistics, I should get an idea what this line looks like. Kind of looks like that. It may not pass through any points at all, but is the closest to all of them put together. Okay. So negative 6, 7, or 6/10, negative 6/10, negative 7/10. What do those numbers mean? It's values for beta naught and beta 1, right? Which is the something and something with respect to the line. Slope and the y-intercept. So if I were to write my line y equals mx plus b, what's my m and what's my b? So which one's which? So remember how we wrote the equation of the line, right? The beta 1 is your slope, and the beta naught is your y-intercept. So which one's beta? Which one's my slope again? 7/10, and then my 6/10. right? So if I were to do this, I hope to get a good picture out of this, right? I wonder how I should do this. I think Excel. After I said I was really good at Excel. How do you do this? Oh, let's do it on a calculator. Yeah. Oh, because that's the coefficient according to your design matrix. Your system of linear equations just have the beta naught, and then to write your system of equations into a matrix, the coefficients of beta naught is what goes in the first part of the matrix, in the first column of the matrix. If you want to redesign your matrix to not have something other than 1 here. Or if I switch the order, I would have x1, x2, x3 times beta naught. I mean, is it going to answer his question? Oh, wait, let me finish answering his question first. So if you would have, and this is, I don't know if this is going to be more confusing, but if you were to write your design matrix as mx plus b, like that, and then we would write our solutions as m times x1 plus b, m x2 plus b. So you want that to equal to y1 to y2, etc. Then your design matrix is going to be, remember that your parameters are the things that you're going to be looking for. And so your x values will generate your first column. Yes. The coefficient of the constant. Right. Yeah. So you can, I mean, you can write it mx plus 2b, and then you'll have something different that way. But if you change your design matrix to exponential functions or something, then it might look different. If you, like I said, if you change your design function or design matrix to use quadratics, I think you're still going to have a row of 1 somewhere. Okay. Question. Oh, yeah. So it's all 1s because of it just happens to be the coefficient. Yeah, that's how you designed it. You could, and then that means your equation would be y, yeah, equals mx plus 2b. Yeah, and then you'll get the same b anyways. Yeah, because you just merge it into the constant. Yeah, the coefficient can possibly be different. So let me see. I forgot how to use this. Your data set for your x values 1, 2, 4, 5, and for your y values 0, 1, 2, 3, 0, 1, 2, 3. And then I think the test here is to do a lin-reg t-test. L1, L2. So I have my A. So my solution is supposed to be A plus, what? y equals a plus bx. So b is your slope and a is your y-intercept according to this. And so a is equal to negative 0.6 and b is equal to 0.7. Did that agree? That agreed with what we did, right? And so now let's also try to graph it. So let's do a scatter plot, L1 and L2, and then let's graph the line as well. Test, stat and test. Okay, zoom stat, zoom fit. All right, what's going on? Oh, I have to turn this on. Oh, come on. There we go. So if I were to draw this graph, it would look something like this. Hey, that looks pretty good, huh? Like looking at my picture. Okay. So is that cool? All right. So now let's take your data. I hope I have your data. Let's switch gears and actually use MATLAB. And let's take your data. I think, how do I do this? Import data. What happened? There we go. So this is the data that we just collected, right? I think I want to put this in column vectors. I'm not going to care about the initials. And I have the foot size and the height. So I think this is good to go. We're imported already, was it? Oh, there we go. So the height and the foot size are here. So if I were to check out the foot size, it's a set of column vectors. If I were to check out the height, it's another set of column vectors. Okay, and hopefully they matched. Is that cool so far? So now I want to create a matrix, our design matrix. We'll call it capital X. Our design matrix is going to be made up of ones. How many data points do I have? It looks like 24 of you guys participated, right? So I'm going to need to create a column vectors of ones and 24 of them. So for my first column, I'll make a ones vector with 24. That's 24 by 1. And then for my second column, what am I going to have? The x values, which would be the foot size in this case. Okay, so that looks like, so I have 1 and a bunch of foot sizes on the second column. Now my y matrix or vector is going to be my heights vector. So just to put it together, let's see, A equals, if I were to solve for it using just the regular solving, I would do a row reducing, right? That would be the matrix X and augment it with a Y vector. And I would row reduce this. Oh. So I see I get a bunch of zeros, but somewhere along the line, right on this line right here, it tells me that I have 0 is equal to 1. So this is clearly inconsistent. Okay. We didn't care about that. We knew that that was going to be inconsistent because we're looking for the line that best fits it, because it's not all going to land on the line exactly. So what did we need to do? What were the things that we need to do? We need, oh, so x transpose x. So x transpose times x. It looks like these are small numbers. And then take the inverse of that. Okay, so we got a 2 by 2 matrix, which we should have expected. And we need x transpose times y, right? So x transpose times y. And then we want to multiply all that, don't we? So our beta vector is going to be the inverse of x transpose times x times x transpose times y. Is that right? Parentheses around. Whoa, 38. Which one's the slope again? Which one's the y-intercept? Which one's the slope? The b naught is the y-intercept. So 38 is the y-intercept. And then this has a slope of 2.9 around 3. All right, let's plot it. How do you plot? Sure, we're going to plot. We're going to plot the foot size and the height. And I think there's some commands where we can make it O and red. And then we want to plot the line. So the line is going to be foot size. And then it's going to be the line, the equation of the line. What's the equation of the line again? It's beta. So the first one, beta 1 plus beta 2 times the x value, right? And then let's color this blue. There it goes. Who's down here? So this one had a foot size of 9 and a height of about 552 inches. What? Instead of 52? I was adding in my head, so it could be wrong. Yeah. The average change. So to interpret that, and we do this in statistics a lot, so the slope is about 2.9, right? So that's 3. So for every inch of foot size you increase, your height is going to increase by 3 inches. So for every inch of foot size you increase, your height is going to increase by 3 inches. That's according to the model. Okay? Pretty cool, huh? Anyways, there you have it. I just sent out an announcement to my stat students, my online stat students, that there's this website, there's a bunch of websites that talk about bad correlation. Have you guys seen any of those? Bad correlation. Isn't that a song? Bad. What's the Lady Gaga song? Bad romance. Oh, bad romance. Bad correlation. Anyways, let's move on. So I have a set of commands that you can try out. You can put in some values for your X list and your Y list, and then you can make up a column list and then create your X matrix and stuff. So I'll put this in the notes for you guys, and then the plot command over here would plot your data points in red, and then would plot your line in blue, as long as you call it whatever it is you call it. So let's move on. The other thing that we were talking about was this whole idea of orthogonal stuff. And forcing an orthogonal matrix out of this is probably going to be more work than it's worth. Because what you're going to do is you're going to adjust it so that your center point is in the middle, or it's at 0 or something like that. But let's say something about it at least. Because this idea will come up again for us when we talk about Calc 3 stuff. Calc 3? What? I thought Calc 3 wasn't a prerequisite. Okay. So, a common thing that people do apparently is to shift their center point, their mean, the mean, sometimes known as the arithmetic mean, or we might know it as the average, although the word average has a lot of other meanings to it. But the word mean in this case is the arithmetic mean. And if we shift the mean so that the mean is equal to 0, then we could have an orthogonal matrix, or we could create an orthogonal matrix. So by doing that shift, this is called the mean deviation form, and the design matrix will be orthogonal. And orthogonal matrices, are a lot easier to deal with. It turns out also that orthogonal matrices, or if you at least have matrices that are, how should we say it, orthogonal, but not necessarily orthonormal. The columns are orthogonal, but not necessarily orthonormal. Then there was something interesting when we took X transpose times X. Remember, in the previous example, when we multiplied X transpose times X, what kind of matrix did we get? No? Well, that's switching it. But what happened when we took X transpose times X in the previous example? You got a what? It's invertible, but hopefully it's all invertible. But what can we say about this matrix, 4, 12, 12, 46? It's symmetric, right? Now, the thing about an orthogonal matrix is that if we do the same move on an orthogonal matrix, then when we do this multiplication, not only are we going to get a symmetric matrix, but it's actually going to be a diagonal matrix. Zeros. So now if we're dealing with a diagonal matrix, that's going to make things easier to solve for. That's going to make things easier to solve, period. The diagonal matrix is a symmetric matrix. It's a special case of a symmetric matrix. It's zeros on the outsides, right? So a diagonal matrix just means we just have numbers in the diagonal. Everything else that's not in the diagonal is 0. And in that case, it's necessarily symmetric. Does that make sense? Is that clear? So in fact, we can kind of mess around with what we have here. see, I didn't plan for this, but let's see if we can work it out. We have our set of foot sizes, right? Let's take the average of the foot sizes. Average, AVE. Oh, mean. Of course, this is a math thing. So the mean foot size is 10.0125. That's our average foot size. Let's call this M. Now, if we take our foot size vector, and what did they say? Subtract it from M? I don't want that. X minus X bar. So I wonder if this is going to do it properly. X new is foot size minus M. It's probably going to give me an error. Nope, didn't give me an error. So if I shift this by subtracting the foot sizes, I have a new list of X values now, right? And the average of that what did I call it? X new should be 0. Well, that's close enough. So now if I use that as my new list, X, capital X new is going to be the list of ones, 24 of them. And my new list, X new, lowercase x new. So I've essentially shifted it so I have a bunch of positives and negatives there. And now if I take the product of X new prime times X new, so X new transpose times X new, I should get a diagonal matrix. Yeah. No, it's not going to span. It's good because now it's restricted to. Well, the span of columns here, this would be. There's 24 of them, right, in our example. So this is an R24. So it's going to span maybe a two-dimensional vector space in R24. So I think in that sense, we're not going to be too concerned about the span of the matrices here. We're looking for the numerical results. We're saying is that what we're saying is that these two column vectors are perpendicular. They're not necessarily of unit length, although we can do that. And if they are of unit length, then your diagonals will be ones, but they're not. So, yeah. To have the mean, when their mean of the X list turns out to be 0, then it's orthogonal. Yeah. And what happens, because we're talking about in statistics, we have the same amount. If you add up, so these are all ones, right? And so there's some value in trying to figure out why they're, that they're all ones. It plays a part in making things orthogonal. So because these are all ones, you're essentially adding just the second column. So 1 times -2, 1 times -1, 1 times 1, 1 times 2. And so basically, if you add column, the second column, and you get 0, then that means that the average is 0. It's like you add them and you divide by the number of numbers, right? So how can you add things and divide by a positive number and get 0? Well, it's only going to work out if you add them and you get 0 in the first place. Okay. All right. We're not going to talk about residuals here too much in this class. Well, but since it's in the notes, there's usually this thing called a residual vector that tells you what the error is for each of those points. So each of those data points has a distance, a vertical distance to the line, and that vertical distance will give you your error. So that's your residual. So let's just pass over that and then go on to the next idea. So just to talk about a couple of other different types of design matrices. Instead of having a linear regression, you could possibly have a quadratic regression. Oh, the formatting is not good here. Let me see. So maybe for the sake of not confusing ourselves, let's not worry about the epsilon, the error. The error is just being added on anyway, so it's not that big of a deal. But let's consider if you're doing a quadratic regression. If you think that your graph looks more like a quadratic than it looks like a line, like more like a parabola shape, then your design matrix will look different. So your design matrix, you'll have y1s through yn's, and you want that to equal to a quadratic formula, basically. And so in a quadratic formula, you have unknowns. You have an unknown constant, you have an unknown linear term, and you have an unknown quadratic coefficient term. And so those are going to be your unknowns, your beta naught, beta 1, and beta 2. And then beta naught is your constant term that's going to have a coefficient of 1. And then your beta 1 will be the linear term and the coefficient of x. And so the x are the x values that you put in. So here's the interesting part, is that your beta 2 is a coefficient of the leading polynomial term, which is going to be x squared. So what you need to do is you need to take your x values from your original data and you need to square each one to produce your third column. So now you have a different design matrix from what we had before. In our original matrix for the linear, we have n rows and 2 columns only, right? For the 2 parameters, beta 1 and beta, or beta naught and beta 1. Now for quadratic, you have 3 parameters you're looking for. So this is going to be an n by 3 design matrix. So it depends on what the parameter, how many parameters you want to get. Yeah. Oh, you just take so the x comes from the data points themselves. So in our case, if we wanted to look at the foot size as the data set, if you ignore the line here and just look at the dots and say, hey, the dots kind of look more quadratic than linear, then I would redesign my matrix. And the x squareds come from the foot size, since that's our x values. So you would change your foot size. Instead of somebody had a foot size of 9, so the design matrix will have 981 or something for that row. Right? So if we take a look at our first example, where we have the points 1, 0, 2, 1, 4, 2, and 5, 3. Then your design matrix here will be x is going to be 1s for the first 1, 2, 3, 4 for the first column. For the second column would be the x's 1, 2, 4, 5, and for the third column would be x's squared. So that's 1, 4, 16, 25. So that's your new design matrix. And then you still have your same beta, beta 1 or beta naught, beta 1, beta 2. And then your y values would still be the same as last time, which is 0, 1, 2, 3. And then when you do this now, you'll have, this is a, the x transpose is going to be a 3 by 4. So you have 3 by 4 times a 4 by 3. So your x transpose times x is going to be a 3 by 3 matrix. And then you have to find the inverse of that, and then you go on and finish the rest of this. Which might seem daunting if you're going to do it by hand, but if you're just going to punch it in the computer, then it's not a big deal. So a cubic polynomial, you can do the same thing. You can extend the cubic. And then in the book, in the textbook, they have examples of an exponential model or logarithmic model and stuff like that. So those are all things you can take a look at. Okay. So now we've successfully applied this to something in statistics, something that we can use in real life, something that we've actually measured and tried out in real life. So, there. The next time we meet, we're going to be in Chapter 7. And Chapter 7 is going to be focused on symmetric matrices. Okay, so get yourselves prepared for that because it's going to be deep. Yeah. Do you guys know how to do this already? Yeah, you'll have a quiz. All right, see you guys next time.